This is the first lecture on solubility equilibria from Chapter 17, Additional Aspects of Equilibrium. Way back in Chapter 4, we learned some solubility rules. We learned that a number of things were soluble and therefore completely dissociated in water. For example, if they included atoms or ions like sodium, lithium, potassium, rubidium, and cesium, group 1, or the chlorides and bromides and iodides were fairly soluble as well. We would write these as solubility equations with a single arrow going to the right, saying that this ionic complex would completely dissociate to form lots of this. And if there was 1 mole of NaBr, there would be 1 mole of Na and 1 mole of Br minus in the dissolved water. But what happens if the substance is not soluble? Does that mean none of it dissolves in water at all? Well, that's not necessarily true, because as a matter of fact, we're worried about different types of toxins being in our water, like lead or mercury or things like that. And so there must be a little bit of it that dissolves in water. And as a matter of fact, this little bit can mean a big difference, as we know, in terms of poisons or toxic substances that are in our water. So let's take a look at something like PbCl2. We know that the chloride of lead is insoluble in water from the solubility rules that we learned. But a tiny bit of it does dissolve. A tiny bit. A tiny little bit. And therefore we don't write a single arrow like we would with NaBr, but now we look at it as it's based on an equilibria, where there's a double arrow here saying that only a tiny bit of this dissolves to form a little bit of Pb plus 2 and 2 Cl minuses. How much of it? Well, that's what we're here to answer with the solubility equilibria section of Chapter 17. To figure out how much there is, we can actually write an equilibrium expression for this reaction. Now remember, this is a solid over here, and pure solids and liquids obviously don't go into an equilibria constant expression. But these are aqueous. And aqueous things go into an equilibrium constant expression, and so we can write the K expression saying that Pb plus 2 concentration times the Cl minus concentration raised to the second power, because there's a 2 in front of the Cl minus, is equal to the equilibrium constant. Now I divide it by the reactants, but of course the reactants are a solid, and of course this is just dissolving in water, and you never put a pure liquid in there as well. This K now is given a special name. Since it's the product or the multiplication of the two ions that are dissolved, this is called the K solubility product constant, or Ksp, Sp standing for solubility product. In Appendix D, there's a big list of solubility product constants for many different salts that are pretty much insoluble as far as we memorized, but a tiny bit of it does dissolve, and we many times want to know what is that tiny concentration that has dissolved. Let's take a look at some sample problems now using this new Ksp, or solubility product constant. First of all, taking a look at solubility equilibria in section 17.4, there's a question that says write the Ksp expression for the solubility product constant of CaF2. Look up the value in Appendix D. So if we have CaF2, and this is a salt that's insoluble, and fluorides are fairly insoluble, we would write a double arrow saying that a little bit of Ca plus 2 forms, and a little bit of the fluoride ion forms 2F minus. And if we write the solubility product constant expression for this, we'd take the products, Ca++, times each other, and raise them to the power of their coefficients. And in this case, we'd put fluoride to the second power. Now we divide them by the reactants, but there are no reactants here that aren't pure solids or pure liquids. And so this is known as the Ksp expression for calcium fluoride. Or we could look this up in Appendix D as well. Second question says, a saturated solution of silver chromate is at equilibrium. Analysis of the solution shows that its silver ion concentration is 1.3 times 10 to the negative 4th. Assuming that Ag2CrO4 dissociates completely in water and that there are no other important equilibria involving silver or chromate ions in solution, calculate the Ksp for this compound. Well, we know that our equation is silver chromate And if we write it, we know it's insoluble as well from what we memorized in chapter 4, but a tiny bit of it does dissolve. And if we write the products, we'll get a little bit of Ag plus, 2 of them as a matter of fact, because there's a 2 down here, and we'll get a little CrO4, 2 minus. If we write the Ksp expression for this, Ksp would be equal to products, Ag positive 1 raised to the second power, because there's a 2 in front of it, times CrO4, 2 minus to the first power, because there's only a 1 in front of the CrO4, 2 minus right here. Now it asks us to calculate the Ksp. It tells us the concentration of the silver ion is 1.3 times 10 to the negative 4th. Well, we can plug this into the Ag plus ion concentration, 1.3 times 10 to the negative 4th. And then we can take and we can square that critter. And then if you take a look at the stoichiometry of the reaction, if silver ion is 1.3 times 10 to the negative 4th, 1.3 times 10 to the negative 4th, what is the concentration of the chromate ion? Notice there's a 2 in front of this one. That must mean there is only half as much, or for every 2 of these, there's only 1 of these chromate ion concentrations. And so really I will have about 0.75 times 10 to the negative 4th concentration for CrO4, 2 minus. So I'll take this to the second power and then multiply it by 0.7 times 10 to the negative 4th, and I'll have my Ksp. Taking a moment right now to punch it in my calculator, 1.3, enter exponent to the negative 4th, square that, and then multiply that by 0.75, enter exponent to the negative 4th. I end up with a Ksp of approximately 1.2675 times 10 to the negative 12th. That's one way of finding the Ksp if you know the concentration of the ions that are in solution. Turn the page, please. There's a few more sample problems involving Ksp to look at. This one said the Ksp for calcium fluoride is 3.9 times 10 to the negative 11th. They asked for the calcium fluoride Ksp back here, and now we don't have to look it up because it's in this problem. Assuming that calcium fluoride dissociates completely in water and that there are no other important equilibria involving ions, calculate the solubility. The solubility, now that's in other words the concentration of calcium fluoride in grams per liter. The thing that we can find, of course, is the moles per liter, the molarity of the calcium in there, and then what we can do is we can convert from moles to grams to figure that out. So we know that we have calcium fluoride, a fairly insoluble solid, dissolving to give us some Ca plus 2 and 2 F minuses. And assuming that it dissociates completely in water, we are going to get initially have none of this and none of this. If I write an ice table for it right here, we are going to gain some calcium, and we are going to gain 2 times as much fluoride ion right here. So at equilibrium, I'll have X amount of calcium and 2X amount of fluoride ion. Now if I write the Ksp expression for this, I know it'll turn out to be the concentration of calcium plus 2 times the concentration of fluoride ion raised to the second power. And I can take these x's now and put them in for each one of the concentrations. I know that calcium is X and the fluoride ion is 2X, but notice I have to square this as well. And this is going to equal the Ksp, which if I look at it up here is 3.9 times 10 to the negative 11th. My goal is to figure out what the calcium ion concentration is in here, because if you look, the calcium ion concentration and calcium fluoride concentration have a 1-to-1 stoichiometric ratio, 1-to-1. So if I find this number of moles, I will also know the moles of this because they're related 1-to-1. I could also find the fluoride, but notice it's a 2-to-1 ratio, and so I'd have to do a little bit of additional math to do that. Anyway, this turns out to be 4x to to the third power is equal to 3.9 times 10 to the negative 11th. Divide both sides by 4, and of course take the cube root of both sides after I divide by 4 here. So, oh, this is the negative 11th, I'm sorry. Then take my 3.9, enter exponent, negative 11th, divide it by 4, and then I'm going to take the cube root of that, so in other words raise it to the 1/3 power, to the 0.33333, and I'll end up with x equaling 2.14 times 10 to the negative 4th. So this is my molarity, or my concentration of calcium ions in solution, which I said is a 1-to-1 ratio for the concentration of calcium fluoride that is dissolved. It asks for it in grams per liter, so I'm just going to work that right over here on this side. If I know the concentration is 2.14 times 10 to the negative 4th moles per liter, that's my molarity, I could convert it from moles per liter to grams per liter simply by knowing the number of grams there are in a mole of calcium fluoride. And I can add that up on the periodic table, knowing calcium is 40, and each fluoride ion, I believe, is about 19, so there are about 78 grams in 1 mole if I add that up on the periodic table. So take that number, 78, times my 2.14, enter exponent negative 4, and I end up with a gram per liter now solubility of approximately 0.0167 grams per liter that dissolve of calcium fluoride. Next one says, you try. What is the solubility of LaF3 in moles per liter if the Ksp of LaF3 is 2 times 10 to the negative 19th? It's a similar problem to what we just did, so pause the video right now and see if you can solve the problem. Okay, if you've returned, now you can see that I'm going to work the problem and you can check your answers. First of all, write the balanced chemical equation of it dissociating in water, even though it's not very soluble. Remember, write a double arrow. Write an ice table. Know that there's no reason to worry about this because this is a solid. None of this and none of this to start with. I'll gain x over here and I'll gain 3x of this. The reason I put a 3 here is because there's a 3 in front of the F minus. So I'll end up with x here, 3x here. And so now I can write my equilibrium constant expression saying that Ksp of it is equal to La plus 3 to the first power times F minus to the third power. And I can put my x's in there. La has an x, F minus is 3x, and don't forget to cube this. And so I'll end up with my Ksp, which is 2 times 10 to the negative 19th, is equal to 3x cubed, which would be 27 times x, so it'll be 27x to the 4th. Now I'll divide both sides by 27, and then I'll end up taking the fourth root of both sides of this. So punching this into my calculator, 2, enter exponent, negative 19th, divided by 27, and then taking the fourth root of that, or raising that answer to the 0.25 power, will give me I'm going to round up, 9.3 times 10 to the negative 6th. And you'll find out in these problems with Ksp that a lot of things are quite approximate. They can be off by at at the minimum 100, sometimes the 10,000 as far as the exponent goes. And Ksp values can actually vary up to 1,000 or more, depending on what your textbook reference is for it. Remember, this is X now, and this would give me my concentration of La plus 3. And notice that's the same as my concentration of LaF. And if it's a concentration in moles per liter, this is it, because this is my moles per liter, this is my molarity of LaF3 in the solution. Next question, calculate the molar solubility of CaF2 in a solution that is 0.01 molar in CaNO32. Oh, in this case now we're taking calcium fluoride and we're dissolving it in a solution that already has some calcium in it. In other words, it has an ion that's in common with the calcium fluoride. Another application of the common ion effect. So in letter A, we're going to take the calcium fluoride, this stuff that's not very soluble, write an equilibrium equation for it, Ca plus 2F minus, and if I just think of it in terms of qualitatively, there already is some calcium nitrate, which is very soluble in there, so there'll already be some of this in there. Remember, according to the Le Chatelier's principle, if there's already some of this concentration in the solution, it should shove the reaction to the left and therefore make CaF2 less soluble. Let's see if it really does. We'll write an ice table, and initially, of course, we have some calcium ion in there. If you look at it, calcium nitrate completely dissociates. It would be a big arrow to the right to form Ca plus 2 and some NO3 minus, 2 of them as a matter of fact, but we don't care about the NO3 2 minuses because they're just going to be soluble in there. And so whatever the concentration of the CaNO32 is, that's the concentration of the Ca plus 2 that's in the solution. So initially we start out with 0.01 molar of this stuff, none of the fluoride ion. Now, when CaF2 dissolves, we will gain X of the calcium over here, and we will gain 2X of the fluoride over here. And so in the end, I'll have 0.01 plus X plus 2X over here. Now I can write the equilibrium constant expression saying that Ksp is equal to my calcium ion concentration times my fluoride ion concentration raised to the second power. My calcium ion concentration is 0.01 plus X. My fluoride ion concentration is 2X, and don't forget to square it. And then this is equal to my Ksp for calcium fluoride, which if I look back to problems I can find out is 3.9. 3.9 times 10 to the negative 11th. 3.9 times 10 to the negative 11th. Well, I can make this a little simpler for myself to solve instead of solving a quadratic. I'm going to say that this x is small compared to the 0.01, and so I end up with 0.01 times 4x squared is equal to 3.9 times 10 to the negative 11th. Divide both sides by 0.01 times 4, and that'll get rid of these guys. And then take the square root of both sides, and I can solve for x would be the concentration of my calcium ion in there. I'm sorry, would be the concentration of my, well, twice, x right here would be 2 times would be my fluoride ion concentration, but I'd take 0.01 plus x to find my calcium ion concentration in there. And it wants to know the molar solubility, so once I've found x, I could divide it by 2 and I'd know the concentration of CaF2, because notice F minus is 2x. So punching this into my calculator, 3.9, enter exponent to the negative 11th, divided by 0.01, divided by 4, and then taking the square root of that gives me 3.1 times 10 to the negative 5th. So therefore x is equal to 3.12 times 10 to the negative 5th. This is my constant, or this is my x value. And if I look over here, 2 times x would be the fluoride value, but regular x would of course just be my calcium fluoride that's dissolved in there, and it asks for what is the molar solubility, and this would be in moles per liter, so that would be my moles per liter that are dissolved of the calcium fluoride, which if we look up above, remember we found out that the molar solubility of regular calcium fluoride was 2.1 times 10 to the negative fourth, a larger number than 3.1 times 10 to the negative fifth. Why is this one smaller? Why did less dissolve in this case than up here in this sample problem? Well, the reason is because there was already some calcium dissolved in the solution, and we said according to Le Chatelier's principle, it should shove the equilibrium back to the left and make the calcium fluoride less soluble, which as a matter of fact it did. Okay, in letter B, it says that there's 0.01 moles of NaF dissolved in the solution. So in this case, if we write the equilibrium constant expression again, or the equilibrium expression of the calcium fluoride, it's going to give us a little bit of calcium and 2 of the fluoride ions right here. And if we write an ICE table, it tells us that it is already initially 0.01 molar in the fluoride ion. When the change occurs, we'll gain x here, we'll gain 2x right here, so we end up with x, 0.01 plus 2x. And if we write the Ksp expression for this now, Ksp of calcium fluoride, once again, is 3.9 times 10 to the negative 11th, and this would be equal to the Ca plus 2 ion concentration times the F minus ion concentration squared, and this of course is equal to x, and this is equal to 0.01 plus 2x squared. And we're going to do some ignoring here to make it a lot easier to work. We're going to say that 2x is small compared to the 0.01. So we end up with an equation of x times 0.01 squared is equal to 3.9 times 10 to the negative 11th. So I can divide both sides by 0.01 squared, divide both sides by 0.01 squared, and then I'll know what x is, and x of course is my calcium fluoride moles per liter that are dissolved, because calcium and calcium fluoride have a 1-to-1 ratio. So on my calculator, 3.9, enter exponent negative 11th divided by 0.01 squared is equal to 3.9 times 10 to the negative 7th, and we can see here now that this is significantly smaller as terms of concentration than what we had for the regular calcium fluoride ion concentration right here back up in the original problem. Why is this one so much less? Well, remember, it's because we have some fluoride ion already in the solution, which shoves the equilibrium back to the left and therefore allows less of it to dissolve. This is an example of the common ion effect in solubility.